Good morning, welcome to new lecture. Today I will solve different sample problems. So let's look at the first example. Assume we have simply supported beam. It is simply supported beam. Cross-sectional area for this beam. It is triangle. Base is, the length is A, height is A, here is point A. This simply supported beam is subjected to concentrated load at mid-span, so this is L over 2, L over 2. We want to find the contraction of the extreme fiber at point A. So what will happen to this beam? If we apply load, this beam will deform like this. So here we will have neutral axis, and neutral axis will pass through the centroid of the cross section. Above that neutral axis, because of this deformation, will be subjected to compression. So we will have compressive stress above that. The extreme fiber, it is here. Extreme fiber has the maximum distance up to neutral axis. Because of the compression in that fiber, in the length of initially the length it is L, we will have contraction. The length will decrease. How much it will decrease? Something like delta. We want to find that delta. First step, we should find the maximum moment in this beam and the moment variation throughout this beam. So we need to draw moment diagram. If this is simply supported beam, here it is load P, reaction will be P over 2, P over 2. So maximum moment will take place at mid-span underneath of this load, and the magnitude will be P over 2 times L over 2, so it will be PL over 4. So maximum moment, it is equal to PL over 4. We know because of the bending moment, we will have normal stress in cross section. Normal stress will be equal to M moment divided by Y, the distance of fibers up to neutral axis, divided by moment of inertia for that cross section respect to neutral axis. Moment here it is PL over 4. Y, it is the distance of this extreme fiber up to neutral axis. That will be 2 over 3A. So it will be 2 over 3A, that distance. Moment of inertia for triangle cross-sectional area respect to that axis passes through the centroid will be equal to if this is triangle, base length is A, the height is B, it will be AB cube over 36. Here because B is A2, so we will have A to the power of 4 over 36. If I simplify this, I will end up with 6PL over A cube. Delta deformation in this fiber perpendicular to the board or how much contraction we will have in the extreme fiber above the neutral axis, because that stress, normal stress, will produce the axial deformation, and we know that is equal to PL over AE, and P over A, it is stress sigma. I can write that is sigma L over E. The sigma stress in that fiber, we find it because of the maximum bending moment. Because of that maximum bending moment, it is 6PL over A cube. But that will take place in the maximum bending moment location at midspan. After midspan and before that, from maximum, it reaches to the zero in the support. So here, moment is zero, so bending stress is zero. It will increase from support to midspan, and then after that, from midspan to the support again, will decrease. The average value, if I want to find the average value, I should convert this triangle to one rectangular, and this rectangular height will be half. So average stress will be half of maximum stress, so it will be 1 over 2 times 6PL over A cube. This will be average stress times the length of the fiber, which is length of the beam is L, divided by Young modulus. From here, contraction in extreme fiber will be equal to 3P L squared over E A cube. This is first example. Let's look at the second example. Assume we have cantilever beam. Cantilever beam, it means we have beam, one side we have fixed support, another side it is free. So fixed support, beam this side, and here it is free. This beam is subjected to concentrated load or point load at free end. If this is point A, this is point B. So reaction here we can find easily. Problem statement asks, find the maximum deflection at free end. So we will have maximum deformation or deflection at free end and slope at free end. So this beam will deform something like this. This will be maximum deflection, and slope here I should draw tangent to the deformed shape. The angle between that tangent to the horizontal direction, it will be slope of this beam at free end or point B. So point B will transfer to the point B prime. We want to find that deformation and that theta, that is slope. In order to find that, I will use double integration method. Of course, there are a lot of methods in order to find that. The first method, because we had that in previous lectures, I will use double integration method. If you remember, I proved second derivative of the y over second derivative of the y over x is equal to m moment divided by EI. If you remember, I proved this. Here, reaction, this reaction, if we write summation of forces in vertical direction, external load is P downward. So reaction here will be P upward. How we will find it? Summation of force in vertical direction. You know that from static. If we take moment respect to the support and we will find the support reaction, that will be equal to PL. So here, now at point A, I have reaction P and I have moment reaction PL. If I cut this beam in the x distance, if I cut this beam in x distance, internal moment mx, I can find it. If I take moment respect to here, the cut point, point O, internal moment will be equal to Px minus PL. What I did, I cut this beam in x distance from left. I have reaction. In this free body diagram, I showed the reaction in the x distance. I want to find internal moment. In order to find internal moment, I should take moment respect to cut point and put equal to the 0. So I will have mx minus p times x plus PL is equal to 0. From there, if I take these to other side, let's say right here mx plus PL minus PX is equal to 0. If I take this to other side, I will end up with this equation. Now, if I substitute mx here, because we know the second derivative of y respect to the x is equal to internal moment, mx, here it is px minus pl over ei. If I integrate this one time, I will find dy over dx. dy over dx in one curve, it is the slope of that curve. So it will be equal to p over ei times x squared over 2 minus lx plus c1. c1 it is unknown. If we integrate one more time, we will have equation for curve. This will be equal to p over ei x cubed over 6 minus lx squared over 2 plus c1x plus c2. Because we integrate 2 times, for each time we end up with one constant unknown. First integration c1, second integration c2. This c1 and c2 initially they are unknown, but we can find it using boundary conditions. So boundary condition, it comes from support conditions. Boundary conditions here, we know at x equal to 0. At x is equal to 0, it means support point. It is fixed support. In the fixed support, its slope is equal to 0. So dy over dx is equal to 0. From here, if in this equation, I put x is equal to 0 and dy over dx is equal to 0, I will end up with c1 equal to 0. At x is equal to 0 again, at point A, deformation or deflection is equal to 0 because beam cannot deform because of this reaction. So from there, I can write yx is equal to 0. From here, if I plug again x is equal to 0 and y equal to 0, this 0, 0, 0, 0, c2 will be equal to 0. So finally, I can summarize here the slope dy over dx equation will be equal to p over ei x squared over 2 minus lx, and beam deformation equation will be equal to P over EI x cube over 6 minus L x squared over 2. So now we want to find the maximum deformation at point B. At point B, x is equal to the L. If I plug here x is equal to L, I will end up with y at L is equal to maximum deformation. If you put here instead of x, L, you will end up with P negative PL cube over 3EI. And we want to find the slope here. Again, at that point x is equal to L, so we should find dy L over dx, it is equal to the theta, and here you should plug instead of x again L in this equation. You will end up with minus PL squared over 2EI. So this will be maximum deformation and maximum slope or slope at free end. This is the way we can find beam deformation or deflection using double integration method. Let's look at another example. In this example, again, we have similar beam. We have cantilever beam is subjected to distributed uniform load. It is subjected to distributed uniform load. The intensity of load, assume it is Q, lowercase q. Here, again, if I cut this beam in x distance and I show the free body diagram, this is the beam length at x distance, external load. Here, again, if I cut it, I will have Vx and Mx, internal forces. From here, if I take moment respect to cut point O, I will end up with, because this intensity is Q, I will end up Mx is equal negative Qx squared over 2. Why? Because if I take moment respect to the O, Mx plus Q times X, so Q times X will be force times that resultant force, it will be at mid-span, so it will be at x over 2. We are taking moment respect to O. Q times x will be resultant force, it will be in x over 2 times x over 2 is equal to 0. If I take that to other side, I will end up with mx is equal to negative qx squared over 2. Again, I will use double integration method. So I know second derivative of y respect to x is equal to mx over ei. I will plug this mx here, so it will be second derivative of y respect to the x is equal to negative q x squared over 2 ei. If I integrate this 2 times, 1 times, I will find dy over dx is equal to negative qx cubed over 6 ei plus c1. If I integrate one more time, I will find yx is equal to negative qx to the power of 4, 24 ei. This is Q plus C1x plus C2. Again, because we integrate 2 times, we will end up with 2 constant unknowns, C1 and C2. We should find these using boundary conditions. Here, again, boundary conditions. It is clear at x is equal to L means fixed support. We know dy at that point over dx, it means slope should be equal to 0, because at fixed support beam cannot rotate, so slope is equal to 0. At fixed support at x is equal to L, we know deformation or deflection in vertical direction, YL again should be equal to 0. If you put here this dy over dx is equal to 0, xl, you will end up here, C1 is equal to Q L cube over 6EI. And if you plug here, y is equal to 0 at x is equal to L, and instead of x, if you plug L and you plug C1 here, you will end up with C2. C2 will be equal to negative Q L cube over 8 EI. Now, we have C1, we have C2. We can substitute this C1 here and this C1 and C2 here. So I should rewrite these equations. If I do that, dy over dx will be equal to q over 24 di minus 4 x cube plus 4 L cube, and yx will be equal to q 24 EI minus x to the power of 4 plus 4x L cube minus 3 to the power of L to the power of 4. These two will be our equation. Let's double check everything to make sure it is right. Yes, it seems right. So from here, now we want to find deformation and slope at free end. At free end, x is equal to the 0. If I plug x is equal to 0, I will end up with y at x is equal to 0 will be equal to negative q L to the power of 4 8 EI, and at x is equal to 0, here if we plug x is equal to 0, this is delta max, theta will be equal to q L cube over 6 EI. Negative in deflection means deform downward, because our y-axis it is upward, so deflection will be negative. Positive and negative in the theta, it shows a direction of rotation. If it rotates counterclockwise, you see here, rotation is counterclockwise, it is positive. In previous example, rotation was clockwise, so it was negative. Let's look at today one stress transformations example using Moore circle again. Assume we have one stress element. Assume we have stress element. This is stress element. Normal stress in the x direction, it is 120 megapascal. Normal stress in y direction, both of them, they are tensile stress, it is 30 megapascal. Shear stress here in x phase, it is, let's see, sorry, this should be 20 megapascal, so 120 megapascal, this is 20 megapascal, and shear stress, it is 30 megapascal, so it is 30 here in this direction, 30 megapascal, and other side will be equal and opposite direction. Here we want to find principal stress. Principal stress, we want to find maximum and minimum normal stress, and in which plane we will, or in which direction we will have that maximum normal stress. In order to find that, we should draw the Moore circle. First point, it is center point of the circle. Center point, it is equal to sigma m and 0. Sigma m, it means average normal stress. It will be 120 plus 20, 140 divided by 2. It will be 70 and 0. Because sigma m is equal to sigma x plus sigma y divided by 2. And because both normal stresses are tensile stress, so we should add together, it will be 70 and 0. Then we should find point B. We will look at to the x phase of the element. If we look at to the x phase of the element, the stress sigma x, it is 120, and tau xy, it is 30, positive 30y, because this shear rotates this stress element counterclockwise, so it is positive. According to my contract, I said different book have different method for positive. I assume counterclockwise rotation is positive. Point C, another point in y phase of the element, normal stress, again tensile stress 20, and shear, it is negative 30, because this 30 wants to rotate this element clockwise, so negative 30. Then we will have horizontal axis, sigma normal stress, vertical axis, tau shear stress, and positive tau, it is downward. Positive tau, it is down. Let's show these points on this coordinate. Center point will be 1 point, 70 and 0. For example, here, point A, it is 70 and 0. Pay attention, center of Moore circle always lies in the sigma axis. So tau for that should be equal to the 0. Always center of Moore circle should be in the sigma axis. So A, it will be 70 and 0. Point B, it is 120 and 30, for example. This point. Point B, 120 and 30. Point C, it will be 20 and negative 30. So 20, negative 30, point C. Now, to the center of A and this radius, I should draw one circle. This circle intersection with sigma, it will show sigma max and sigma mean principal stress. Tau max, it will be equal to the radius. Tau max will be equal to this height for right angle triangle. This height, it is 30, the square root of 30 squared plus this leg. This leg will be 120 minus 70 squared. So 120 minus 70 squared. So this leg, it is 30. This leg, it is 50. From here, tau max will be equal to 58.3 megapascal. So R will be equal to tau max. That will be equal to 58.30 megapascal. If we rotate point B as much as 2 theta P, it will become sigma max. So it will rotate point B, this face of element. Theta P counterclockwise. This face will be toward to the maximum normal stress. So 2 theta P will be equal to inverse tangent of 30. Inverse tangent of 30 divided by 50. From here, 2 theta P will be equal to 30.96 degree. From here, theta P will be equal to 15.48 degree. Because, as I mentioned, rotation in Moore circle will be 2 times of real rotation of element. Now, let's find sigma max. Sigma max will be sigma mean plus R, that is equal to 70 plus 58.3, it is equal to 128.3 megapascal. And sigma mean is equal to sigma m, mean stress, minus R. That will be equal to 11.69 megapascal. Now I have the magnitude of maximum normal stress, minimum normal stress, we call it principal stress, and the orientation or direction. So I can show here. So if I rotate this element 15.48 degree in this direction, you will have maximum normal stress 128.3 megapascal, and in this direction you will have minimum normal stress magnitude 11.69 megapascal, 11.69 megapascal. Because rotation here clockwise, if we want rotate B and bring the point B to here, the maximum normal stress point, we should rotate counterclockwise. So here I will rotate this element counterclockwise. Okay, let's look at another example. And so we have one simply supported beam. Subjected to concentrated load at midspan P. The cross-section area, cross-section for this beam, it is one square shape. The side of square, each side it is A. And so we bought one lumber. The lumber, it is square shape. And each side, it is, for example, 2 inch by 2 inch. It is A, I assume. I can put this beam in this position, or I can put in this position, like this. I rotate this, and I put in this position. Which one is better? In order to find which direction we will put it is better, we should find section modulus. What is the section modulus? Here, this beam will deform, and deformation will take place because of the bending moment. So bending stress, it is equal to my over I. Here I can write this formula like m over I over y. It is the same thing. This I can show with S. So S will be equal to I divided by y. We call it section modulus. Or sometimes they call it elastic section modulus. Elastic section modulus is a geometric property of the cross-section. It is similar to cross-sectional area, similar to moment of inertia, so it is geometric property of the cross-section. And bigger one, if it is bigger section modulus, if here is bigger, bending stress will decrease, so we will find better position to put our beam, because if we produce less bending stress means there is a gap between that bending stress up to allowable one. We can increase the load, or the section or the beam is stronger. We should try in design minimize the bending stress. So we should produce less bending stress in section. Now let's calculate section modulus for both this section. Here neutral axis passes through the centroid, so neutral axis will be here and neutral axis will be here. I will call this is position 1 and this is position 2. So I will call this case 1, case 2. Let's look at each case one by one. In case 1, A. So from here to here, it will be equal to square root of 2A, and this height will be square root of 2 over 2A. We should know moment of inertia for triangle respect to the axis passes through the base. If this is A, this is B, it is A, B cube over 12. We can calculate this. And if you look at the appendix in the static book, you will find that here. So we have two of these, one here, I. For this will be equal to 2 times of base length, it is square root of 2A times height cube square root of 2 over 2a cube over 12. If we simplify this, this will be equal to a to the power of 4 over 12. From here, S for case 1, this one, will be equal to, it is I over y. I is a to the power of 4 over 12. Y, it will be the distance from extreme fiber up to neutral axis. It will be a square root of 2 over 2. This will be the square root of 2 a cube over 12. Let's look at today this case 2. Case 2, it is a square shape. The square shape, moment of inertia, it is a to the power of 4 over 12. And the extreme fiber distance up to neutral axis, it is a over 2. The answer for this, if we simplify, it will be a cube over 6. So the ratio of section modulus 1 to section modulus in case 2 will be equal to 1 over square root of 2. This will be equal to, I can write square root of 2 over 2. So this is the way we will calculate section modulus. Section modulus means moment of inertia. Section modulus means moment of inertia divided by the distance of extreme fiber up to neutral axis. Using this, we can calculate which direction, which cross section is stronger for beam application. Let's look at another example. We have two simply supported beam. This beam is subjected to two identical concentrated load at the distance of A. Cross section for this beam, it is a square shape, it is A and A. And the external load magnitude, it is P and P. Another beam, it is the length is the same, but at mid-span, we have concentrated load 2P. So beam is the same, the length of the beam is the same. Here we put one load here, another load here. Here we combine two load and we put in mid-span. And we put the same beam in this position. So here it is bending respect to this axis. Here it is bending respect to this axis. This is again A and A. We want to find, this is case 1, case 2, we want to find the ratio of bending stress in case 2 over case 1. In order to find that, let's look at case 1. sigma 1 will be equal to m. The maximum moment here, if we draw the moment diagram for this shape, it will be like this, and here the magnitude will be p times a. The maximum moment, it is p times a. Y, the distance of extreme fiber, it is a over 2. I will be a to the power of 4 over 12. So if we simplify everything, we will end up with 6p over a squared. For this case, or for this scenario, we will have sigma 2 is equal to, moment diagram for this will be like this, and here the maximum moment will be p times 3 over 2a, so it will be 3pa over 2. Let's see, I'm right, yes, here it will be p, so p and p times 3 over 2a, it will be 3pa over 2. So maximum moment will be 3pa over 2 times distance of extreme fiber up to bending axis, it will be square root of 2 over 2a. So here we will put a square root of 2 over 2, and I here for this kind of diamond shape will be again a to the power of 4 over 12. From here this will be 9 square root of 2p over a square. If we plug here, this ratio will be 3 square root of 2 over 2. Okay, these were different example problem. I solved it to see how you can approach to these kind of problems. I think it is enough for today. Thank you so much for watching this lecture. See you next session. Bye bye.